Differential equations were in section 1.2, our first day, day 1. It's honestly a section that you've done in Calc BC. I can solve differential equations with initial values given. At least that much you certainly have done. A little bit of new material. You can determine an interval for a solution. That's something that we will be talking about. That's a new component. So initial value problems, if it sounds familiar, you've done them before, we are often interested in solving a differential equation subject to prescribed side conditions on y of x or its derivatives. So, for example, you might be asked to solve a dy dx is equal to some function, and you are given an initial condition. You're given that when x is a certain value, y is a certain value. What will that allow you to do? Well, it will allow you to find what a constant would equal. Let's say we had a second order initial value problem. You're given a second derivative is equal to an f of x, y, and y prime. Well, you'd be given two initial conditions. You'd be given a beginning x and its corresponding y value. Likewise, a beginning x and its first derivative y value. So notice, with that second derivative, we're actually going to need two components. Likewise, if we were to have an nth order, if you had the nth derivative, well, you'd have to have quite a few initial conditions. You'd have to have a y prime initial condition, a y double prime, all the way up to the derivative right before the nth derivative, the n minus 1 derivative. So let's take a look at something that you honestly have done in the past. You've done problems just like this. Y double prime is equal to x. Well, let's go ahead and take an antiderivative. This is a separable, differential equation. Bump our power up, take an antiderivative. We'll have x squared all over 2 plus a constant. I'm going to call it C1. Now, off to the side, I do want to call your attention to this initial condition. It means that when x is equal to 0, y prime will equal 3. So I'm going to let 3 go in for y prime. Here's 0 squared over 2 plus C1. You can pretty much see immediately that C1 is going to equal a 3. What does that really tell you? It tells you that your first derivative is x squared over 2 plus a 3. Well, now you know what your first derivative will equal, but when they're saying solve, they actually want you to find what y itself will equal. So let's take an antiderivative. We'll bump that x squared up to x to the third, divide by a 3, put another 3 down below. 2 times 3 will get you a 6. And then we'll say plus 3x. And of course, we'll have a second constant. But now with this initial condition, we're saying, look, when x is equal to 0, y will equal negative 4. And we're going to plug that in. And the reason we're plugging it in, of course, is so that we can find what that constant is. And you won't always be given, an x value of 0. That will complicate matters slightly. And I do say slightly just in that you have to do a little bit more solving. But now you have a particular equation right here. But I do want to make this comment. We might as well start talking about the interval of which you have a solution. You could think, what do you mean? Well, what kind of x values do you think this is going to be good on? I'm going to say it's good on all of them. So that's that second component of our learning target, finding an interval that would represent your solution. You might think, why in the world is it negative infinity to infinity? Well, your function is never going to be discontinuous. So here's what we're going to do. We're going to take a look at this second page real quick. And here on this page, we're really going to take a look at a new issue. Take a look at this solution. Let's just say that you come up with this for a solution. Eventually we will in this class. Y equals 1 over x squared minus 4. Of course, that denominator factors into x plus 2 and x minus 2. And at that moment, you're going to see your function is undefined at a 2 and at a negative 2. So if I may, I'm just going to real quickly draw an x-axis. And more or less what we're saying is it's not okay to plug in a negative 2 or a positive 2. And what that really is saying is that our x-axis here, or our possible x's, are going to be broken up into 3 possible regions or intervals. We're going to say, look, you could have x values bigger than 2. You could have x values between negative 2 and positive 2. You could have x values smaller than negative 2. And that's really what we're saying right here. We no longer have a continuous domain, so to speak. So we're either going to be from negative infinity to negative 2, from negative 2 to 2, or 2 to infinity. You could think, well, how in the world do you know? The interval of solution depends on the initial condition. So look at this. If we had y of 0 equals negative 1/4, what this is really telling us is x equals 0 is your initial condition. And that means the interval that we'd say that our solution is valid on only can go from negative 2 to 2. Likewise, if we were to look at this, that y of 5 equals 1 over 21, this is saying x is equal to 5. And x is equal to 5 is over here in green. The interval of solution, we'd say, hey, our function that solves the differential equation is y equals 1 over x squared minus 4, but this is only valid from 2 to infinity. Finally, if we had y of negative 3, notice I'm not even looking at that output. I'm just really focused in on what x is. The initial condition is x equals negative 3. Guys, negative 3 is right here in this yellow region. So what interval are we going to have? Well, negative infinity to negative 2. So that's really what we're talking about right here. When a function has discontinuities, we have to be very, very specific about which interval is going to be represented as a part of the solution. The initial condition is going to nail that down. So believe it or not, that is lesson 1.2, day 1. Good luck.